Okay, cool. So now I'm going to switch track and switch to learning causal models. So again, this is from the same, I'm continuing from the same books, Elements of Causal Inference and the Causality text. The algorithms I'm going to be talking are rather old, actually. It's about 15 years old. There's been developments beyond that, but I'm going to talk about those with theory. There's a lot of heuristics in this space, and you will see why, because this problem is quite messy to learn this model. So I'm not going to talk about any of the heuristic algorithms which have been developed in the last 10 years. I am just talking about the sort of an exemplar of two different styles of algorithms. That's really the take here. This is not meant to be state of the art in learning models. Okay. All right. So given that, the outline is, first, let's see what we can learn with infinite data. So again, here, I want to learn causal models with infinite data. You'd think that's an easy problem, but even that is complicated. We'll see what the issue is. Okay. So suppose we are given a DAG, okay, and a joint distribution over the random variables x1 through xd. And before we do learning, is there a structural causal model that is consistent with this? You see the question? I've given you the DAG structure. I've given you the graph structure. And I give you a joint distribution as well, the P function. Okay, I give not just structure, I've actually given you the joint distribution. Okay. That's consistent with the G, meaning that that joint distribution has a factorization, Markov factorization, that is consistent with this graph structure. Then the first proposition is you can reverse engineer and actually find a structural causal model, a generative model, that results in a P with a Markov factorization by G. I'm not showing the proof here. You can read it, but it's pretty straightforward because it's just iterative. Okay, because it's a DAG. Start from the root, the topmost nodes. Just make sure that you define a random variable whose marginal is exactly what you want. Then look at its children, and then you got that already. Build a conditional distribution. Write an equation to give that conditional distribution and work top down. Okay. So you can doesn't mean this is the real structural causal model which quote unquote generated the data. I'm just saying there is a SEM that is consistent with it. And this discussion, what I had, it's clear that the proof, I mean, it's just bookkeeping. It should be doable. All right. Now, the second question is, given infinite samples from this joint distribution, can we actually recover the graph? And the answer is no. We go back to our problem of faithfulness, right? In particular, we already argued that we cannot, with infinite samples, distinguish between these two structures, okay? Because essentially, x and y, z, could be independent if c plus a times b equal to 0, okay? Yeah, specifically, these are jointly Gaussian, and x and z are uncorrelated. We just play with variables. Look at the correlation of x and z. You'll get an equation for that when you compute the correlation, the correlation coefficient. And in that, there will be a term, the numerator of the form c plus ab. And just if that is equal to 0, then the correlation coefficient is 0. And therefore, because they're jointly Gaussian, it also results in independence. Yes.
I can essentially think of this as saying that there are multiple DAGs that are consistent with my joint distribution. And then I can possibly only recover one of them at best.
This is actually even more. Yes, but that is true. That doesn't even. Good. There are multiple DAGs, but there are multiple DAGs for multiple reasons. That's what I'm trying to say. Okay. This is actually a big reason. We'll see other reasons as well. Okay. This is saying that in this case, even the directions, lots of things change here. This edge goes missing. This direction changes. So look at these two graphs. They're very different DAGs. Okay. And from infinite data, you can play around with A, B, C, and A tilde, B tilde to make these things have, from the sample point of view, the joint distributions look simple. Yeah.
Yeah. So from causal inference perspective, is the right one preferred than the left one?
No. From a causal inference perspective,
So it will be easier to come up with a valid adjustment set using the right one.
But that may not be true. So from a causal inference perspective, the fix is the assumptions. Assume this doesn't happen. Okay, that's what people. The standard assumption here is faithfulness, because we can't distinguish between these two. Yes, the one standard assumption is saying, hey, C plus AB is a zero measure set in this in R3. Meaning, look at all possible values of AB, C, okay, in R3. And this condition C plus AB is right. It's a zero volume set in this in space. And so we will just assume that some quote unquote general position like assumptions will take care of this. Okay, I'm being very sloppy with words here. Just an assumption. Yes.
Can we go to previous theorem? In previous theorem, does it mean there is only unique?
No, I didn't say there's anything unique. You can make. I said there exists ASA. There's no uniqueness claim here. This is not necessarily just like go back to random variables. If I give you a random variable, can you construct an omega FP consistent with it? Yes. But does it mean that's a unique construction? No. Okay. Yeah.
I just have a quick clarification question. So I'll utter three statements. Can you tell me if it's like true or false? So given a joint distribution, I cannot distinguish between those two tags.
Oh, now you're going to this one. Okay.
Yeah.
Yes.
Given infinite samples, I cannot distinguish. But given a Markov factorization, I can. Because through that factorization, I'll construct the...
Yes. The Markov factorization is saying this is the graph structure. You're essentially, the Markov factorization is the structure. If you think about it, it encodes the structure exactly. Okay. Yeah, exactly. So, yeah. All right. So we have this issue. So what if we impose faithfulness? That is, we are given infinite samples from P, and further, we are guaranteed that this does not happen. Then can we actually learn the graph structure? Even then, not quite, but this is what we can show is the following. Remember our statement of CP DAGs previously. So I'll just recall the CP DAG because we did it on Tuesday. Okay, is the completed partially directed acyclic graph. Okay, so remember two graphs G1 and G2 are Markov equivalent if they are the set of distributions consistent with the first one is the same as the set of distributions consistent with the second one. Okay, what I mean by consistent is the set of distributions corresponding to a graph is all those joint distributions which have the global Markov property with respect to G. Okay. Then CP DAG was then we then talked about Markov equivalence class. That is a set of all DAGs that are consistent with G. Okay, and so, and the key result was that G1 and G2 are Markov equivalent. This is again from I just insert this from Tuesday's lecture. Okay, G1 and G2 are Markov equivalent if and only if the graphs are the same skeleton and the same immoralities, and that gives you a CP DAG. Okay, so what the main result says is here that there does not exist a graph outside the CP DAG such that P is Markovian and faithful with respect to G prime. So the ground truth say is G prime. Okay, so essentially essentially the summary of the statement is if you have faithfulness, then we can learn the CP DAG if you have access to infinite samples. That's what you can get to. Okay. All right. So now that we can learn CP DAGs with infinite samples, how do we go about doing it? Okay. There's a lot of stuff you can read about this. I'm just picking and choose. I've just picked very classical, much older algorithms to give an idea. There I've put a bunch of references, including survey articles, if you want to see where we are in terms of these methods, different types of methods, and so on. At a very high level, there are two types of methods: non-parametric and parametric. Parametric meaning I'm going to make additional assumption. I'll say jointly Gaussian with something else, or non-Gaussian. Okay, I will put some distributional assumptions on the data, and then do then I can try to do some parametric fitting. Or I can say I don't make any assumptions. I just get the data, and I need to cite the structure. Okay, so I'll give you an example of each one of them just to get a sense of how you go about this stuff. The classic algorithm in the space is the PC algorithm. This is in this paper by Peter Spertus, Gilmore, and Shines. Can look at this. The idea is the following. This algorithm assumes black box access to a conditional independence tester. What do I mean by that? I have a box where I can give it scalars x and y. Scalars are vectors, but right now let's just say scalars. Scalar random variables x and y, and a vector z of random variables. Then this returns one of these two statements. X and y are conditionally independent given z, or x and y are not conditionally independent given z. This is the black box. Again, we are also assuming noiseless access to the CI tester, okay, in this thing, meaning it's going to return the statement always correctly with no error. Okay? That's the assumption here. Okay. With finite sample, of course, this is not true, but that's the right now in the learning. That's why I want to start with the infinite sample issues before I go to finite sample issues. I'm going to spend at least an hour, maybe more than that, maybe even 2 hours on just CI testing. That's my plan. Okay. So right now, I'll just call it a black box, and then we'll get into this black box either in the next hour today or maybe tomorrow morning, depending on how far I get. In practice, these algorithms are noisy, and faithfulness is a huge issue because of the noisiness. But we'll get, this is the practical issues. If you want to read more about non-parametric CI testing, I've put one reference here, a kernel-based test, but we're going to actually discuss this algorithm and several others in an hour, okay. Which is what Note 8 is. Note 8 is just CI testing, essentially. Okay, let's get back to PC algorithm. The PC algorithm is, you first learn the undirected graph using a CI tester, and then orient edges according to certain rules. Okay, we'll see it's a two-step process. So how do you learn this structure? Well, there are two immediate properties. There's a lemma, but the proof you can see almost, hopefully, given the discussion, you can hopefully see how the proof should go. If there is a pair of nodes which are adjacent, okay, they cannot be deseparated by any subset. Okay, property one, right? If you got a node here and some other node here, whichever way the orientation is, whether it's this way or the other way, okay. Well, whatever you condition, whatever other set you choose, you cannot deseparate because there's a direct one hop path between the two. Okay, that is one option, one statement. And remember, we are assuming faithfulness, meaning deseparation is the same as conditional independence. We are assuming that it's an if and only if. So anytime you say deseparation, the box I will use to test for that is a CI test. Okay. Yes.
Faithfulness, is it always violated by only zero measure level, or can be violated by?
So that's again so the paper I would suggest you look at for this problem. This question is by the reference I gave by Carolyn Wooler et al. It says that even if faithfulness is a zero code, I don't know. See, zero measure is a bad word because I do what measure. It's in this example is a zero measure set. Okay, they say that what they show essentially is this statement. Let me go back and where did I have? Yeah, this paper, Uller, Raskuti, Bullman, and you, geometry of faithfulness assumption and causal inference, annals of stats. So they show that the volume of structural causal models, which are close to what do volume mean? Please, I'm being very vague here. That are close to one with faithfulness violation is actually a large constant fraction of all linear receipts. So even that means small perturbations are there's a large it's very hard to sort of faithfulness assumption is actually a bad one unless you have so many samples that you can make the small, you can shrink even further down.
So if I understand, if we have infinite sample, this might be okay. But when we have finite, that's
exactly. So for my understanding, because my own research is sort of the finite sample side of things. So I'm not completely up to speed on exactly the infinite sample issues. But my understanding is that people assume faithfulness without too much worry until sort of mid 2010s, when actually you started thinking about finite sample issues. But maybe I'm wrong. Okay, that's just my understanding. The key properties, as I said, if X and Y are adjacent, they cannot be d-separated. And the second, suppose X and Y are not adjacent, that implies that they are d-separated by either the parents of X and or the parents of Y. Okay. Let's look at pair of nodes, X and Y. Okay. If suppose these are the parents and I condition clearly on these two, I mean, I choose these two sets. Okay. Then in downstream, the only way there will always be a collider, so they cannot go downstream. And anything upstream, this union of these two sets separate them, or maybe even one is enough. It depends on the situation, right? So these are two properties which are almost clear, immediate. So the algorithm is an immediate. The zeroth order algorithm is an exhaustive search. Pick any X and Y, search over all subsets using CI tester exhaustively to check if X and Y are condition independent given Z. Okay. I'm basically trying to use property one. Is it clear what I'm trying to do? Pick an X and Y and see if I can find a Z such that I search over all possible Z's to see if X and Y are condition independent. If I cannot, then I'll put an edge between X and Y, and then iterate over all pairs X and Y and over all subsets. It's an exponential brute force search. Yeah, I'm sorry. That's all it is. It's just a brute force search. This is the obvious thing you would do. PC algorithm is a structured way of executing the search. Okay. It uses property 2. That is, if you can find a set Z such that X and Y are conditionally independent. If X and Y are conditionally independent given Z, then there is no edge between X and Y. Okay, because you have found such a set. So so the algorithm is the following. Start with the complete undirected graph over all variables. Set K, the counter, is the cardinality of the size of the set. Initially, set K equal to 0. So you don't condition anything. For every pair of nodes, check for conditional independence. Okay. If you find if you find a pair of nodes which are condition independent, then delete the edge between them.
In the set there can be many sets.
First, yeah. First there's an empty set. I'm the iteration over the size of the set. Initially, I'll start with null set, so there's just one null set. Okay. It's not a very okay. It's a brute force. It's a structured brute force search still. Okay. Then set K equal to 1. For each triplet of nodes X, Y, and Z, check if X, Y, and Z, X and Y are condition independent given Z. Meaning I scan over all sets, all things of cardinality 1. If so, delete the edge between X and Y and iterate. Yeah.
So we are assuming that we have the exact number of variables that
I know the variables. There is no latent. So this is all in the non-latent case. Okay. There are no latent variables, and I have infinite samples. I have a perfect CI tester, and this is how I would use this to execute an exponential search. Hopefully, if the graph is nice, this algorithm will stop when K is small. Okay. But in the worst case, this is an exponential search. Okay. In some sense, this is also state of the art. Okay. Without any assumptions, there are newer algorithms with. There are also lots of heuristics on this stuff, how to deal with it. But I leave it. But I'm just giving you a flavor of how you would search, how you would go about finding these things.
I have a question regarding the algorithm. So for different chosen size of set Z, it may happen for some chosen size X and Y can be not independent, but for others.
That's why this is this structure. I delete edges. So so I've already deleted. I'll not put back edges ever. It's first I check with set size of 0. If X and Y are independent, then I delete that edge. And now I have a resulting graph. Now look over. So I don't need to test with this X and Y already. I don't test this X and Y with some Z, with a Z of cardinality 1.
Why not? Like
Because I've already found that there's no edge between them two. What else can I learn?
like conditioned on some other Z, they can be dependent. So there can
That's so what? That doesn't mean there's an edge. We have already seen that that adjustment sets are not monotone. So that's why it's starting from small size to large size. That ordering is important. Yes.
You said hopefully this algorithm ends quickly, but it will have to run until at least
Yeah.
n-2.
I'm saying hopefully. I didn't say
But I mean, it will have to run until there, because as long as there is that.
if you know sort of this, if you know something else that degrees support the graph, if you know something about the graph that is small degree or something like that, you could, and you find a structure with that count. That again, there's a lot of assumptions you could make on some side information, and which could find maybe better termination conditions and so on. Okay. But in general, this is just the basic. There's a bunch of updates on PC. I'm just giving you just the raw PC. There are much more optimizations on top of it, but still, my understanding is in the worst you don't get around the exponential thing. Yeah.
So for the example of k equal to 1, and we're looking at two different triplets, x, y, and z1, and x, y, and z2. So my essential question is that as we iterate through these multiple triplet subsets, can't we learn something from one subset and apply?
You might. There's lots of other optimizations you can do. But that's why I said I'm just giving you a base algorithm. People have thought about all various speedups, but it doesn't break the exponent. It doesn't change the exponential issue. That's why I just gave this one algorithm as a. Yes, you're right. There are a whole bunch of other relations you can use to get rid of maybe constant fraction of these things.
It won't come away from the.
Yes, that is the real problem. That's the one. That's why I focused on the simplest algorithm to talk about, or the original algorithm. There's a whole line of literature in this, and if you want to sort of couple of references I put earlier, you can look at it to see where the state of the art was at that point. Yes.
You mentioned two key properties, right? You're only using the first one.
I'm using the second one for PC. The first one was the straight brute force. The second one is what PC is using.
What is? What are you using the second one?
Because I start with the complete graph and start deleting. I'm not starting with an empty graph and adding.
The second one is about the parents, right? We're not even talking about the parents.
They're deseparated by some set. This is some set. You can just think of this as a set. If X and Y are not adjacent, they're separated by some set. Yes.
It's only one direction.
Yes. So I'm using the other way. So if I can't, then they're not.
Oh, okay.
So this is basically the property I'm using. If we can find a set Z such that this is true, then they are not neighbors. That's the property I'm using. Yes.
So you're assuming perfect condition independence.
Yes.
In reality, they will have some false positive, something like that. And now since we have exponentially high number of, how would they say it's multiple this correction needs to be? And yeah, is that not? It's like
This is, well, you need how many yeah. I mean, you're pointing out all the real issues, which is why CI testing in practice is not finding these structures, especially with weak edges, quote unquote, is not an easy problem. Is the edge strength weak? Is there a faithful violation? Is this noise? There are so many statistical issues there. I am avoiding any statistical issue in this, and because these are statistical issues with CI testing, and I want to spend an hour plus just talking about CI testing just from a statistical perspective and an algorithmic perspective next, which is why I sort of separated black box, let's assume noiseless access, deal with the algorithm, and deal with the CI tester separately. And then you can put these things together by that. Yeah. Okay. So right now, I'm just going to do this noiseless. All your issues which you bring up are valid. We'll just wait for another hour. Yeah.
This might be a live question, but I'm just trying to understand that we start with all the edges. Like I think that would be in choose edges. So let's say if we don't end up
deleting some edges which should had ideally be deleted.
Okay.
What are the kind of problems that we'll run into if we?
I haven't really thought. It depends on the application is my answer. I'm not sure what you ask. And perhaps people have, because there's a whole bunch of other algorithms. I just gave you the first, which if you know some side information or you know some things don't matter, perhaps you can do more improvements. Okay. But I don't have any better answer than that for you right now.
So, assuming preschool that when we finish this algorithm, you don't have any edges that are left, not thoughts, right?
Yeah, because if I actually do the exhaustive search, then I will get the right undirected graph. That's all we can say at this point.
So are there any lower bound results that in the worst case you cannot beat text?
I think so. But I'm not immediately sure. I can talk offline about some of these things. Second issue is orienting these edges. And there are set of rules which are known to be complete. These are called Meeks rules. Okay, I'm not even going to go through I don't even know them fully. I'm just telling you that there is a set of rules. And this is an edge orientation thing. That suppose you have a graph like this. Okay. Let Z be a set of nodes that d-separate X and Y. If this node Z is not in that set, that means this must be the graph system. Because it's a conditioning on a collider makes them independent. Okay, so you can use your CI test which you have previously along with these properties, to find colliders. Okay, and once you have colliders, you can reason about some of the other edges as well. I'm sure you can think you can. So once I have these colliders, now there's some other node, so I can figure out which way the arrow should go for that one. Okay, but there will be some, but you can only go up to the CP DAG. After that, you can't orient the other edges. Okay, so summary is using that d-separation is the same as conditional independence and exponential number of calls to a CI tester. We can learn the structure in an infinite sample set. That's with no assumptions. I want to give you a flavor of an algorithm where you put much stronger assumptions and you can do something else. Okay, this exponential issue doesn't come up. Instead of allowing any CP DAG, suppose we say that the structure SCM has some structure. Okay, then can we do say linear? It's a linear SCM or something like that. Actually impose those FJs in the SCM are actually linear. Okay, suppose I put a linear model, then can we do some matrix inversion type, some matrix based algorithm to learn the structure completely. Okay. That's a different way of doing this stuff. So I wanted to show one in this style, which is for linear non-Gaussian models or LINGAM. So this is the paper. This is a linear non-Gaussian acyclic model for causal discovery, JMLR 2006 by Shimuzur. So the model is the following. The structural causal model is Xj is some linear function of the parents of that variable plus some noise, where the noise are mutually independent. Okay. And further, the noise are not Gaussian and not degenerate. Not degenerate meaning it has a strictly positive density and variance is one. We'll normalize the variance to be 1, but it's also not Gaussian. So what does not Gaussian mean? Okay, really what the property which will be used in the algorithm is that the joint PDF is not rotationally symmetric. Okay. The Gaussian has a circularly symmetric joint PDF. It will become more clear as I go to the algorithm what is the what property we use for non-Gaussianity. So this is called the yes.
Just one question. So you only assume something on the joint PDF. So one of those variables could be a Gaussian. It suffices that some other one is non-Gaussian and you're good. Or do you need each possible combinations of those noises to be non-Gaussian?
That's a good question. I don't know.
Okay,
I don't.
Thank you.
Okay. But we can go back to the paper and check. I don't remember right now.
Yeah. Okay.
Thanks. So I use the Strider algorithm and maybe
towards the end, we can just figure this out real time. Okay, I'll tell you what, you'll see what property we need, and we can reverse engineer to answer your question potentially. But let me first run through the algorithm and show how this works. So this is essentially, you can learn the structure using something called ICA. So I'm going to describe ICA. If you haven't seen ICA, some of you might have seen ICA already, but in any case, I'll just run through ICA. Okay. This is the model, right? It's a linear model with some noise engine. It has a density, so it's a continuous. These are continuous random variables here. So we have two vectors, x1 to xd, and again, I assume I have infinite samples. Or we can do it with finite samples as well. Then you have to do all the noise stuff. But let's say we have some samples of this. We have this is what you observe. Underlying this is this noise, which is generating this model, but we do not have access to this. Okay, we only have access to this. And so in matrix form, this is essentially the equation we have. We want to solve this, x equals ax plus n. Since the model is a DAG, we can always re-index these variables x1 to xn so that a is lower triangular. Because it's I can re-index it to get that form. That's not a problem. Which means that I can write x is I minus a inverse times n. Good. And I'm going to call this as B. So the goal is to learn B. Indeed, if you actually had samples of noise, this is a standard problem. There's nothing fancy here to learn this B. There's a whole bunch of literature. The problem is that we have only samples of X. We don't have samples of N beyond the fact that we know it is, let's say without loss of generality, zero mean. If it has mean non-zero, we can do some centering and get rid of it. So I'll just assume that N is zero mean and unit variance. So that's an assumption. Okay.
How did you get I minus A inverse?
This equation, I just take AX to the other side. So it's IA minus IX minus IA, and just take the inverse. And it's lower triangular, so it's invertible.
Oh, I see.
Right? So starting from this, I can get this. And this is what we're going to call B. If the problem is, we don't know either one of these, but we want to recover this. Okay, that's the question. But we do know that this is non-Gaussian, and we'll see that that's going to be crucial in actually figuring B out. So B is some real matrix. Let's write it as U lambda V transpose, where U and V are unitary matrices and lambda is some diagonal matrix. Okay. Can always write this. So what is X transpose? I stick it in. X is U lambda V transpose N, and X transpose is the transpose of that. So N transpose V lambda U transpose. Now, N is independent, zero mean, unit variance. So I will take expectation of both sides. What does it mean? This is something I can compute. This is a sample covariance matrix. Okay, zero mean, so it's just a correlation, but I'm just using correlation covariance equivalent. So this is known. If I have infinite samples, I know this exactly. If I have finite samples, I have some noisy version of this. Okay. Good. Take expectation on this side, linearity of expectation, I put the expectation in because this is only random part, and this is just identity because I'm assuming unit variance. So I replace this by I. Now, once I replace this by I, V is unitary. So this also collapses, giving me V transpose V is also identity. Okay. So what happens here is that EXX transpose is U lambda square U transpose. Are you with me so far?
So why is the expectation of N transpose is identity?
Because I assumed that the N is independent across variables and they're all unit variance. So this is the covariance matrix for N, and the covariance matrix must be identity. Is that okay? All right. So this is identity, and so I have expected value of XX transpose, which is a square symmetric positive definite covariance matrix, is U lambda square U transpose. But this I know how to figure out. I have this. I want to find U and lambda. I can do that. Well, I can find U and lambda square up to sign by using PCA. Okay. So I can run PCA algorithm. Okay. And we can learn lambda square and U. So far, good. So at this point, we know the magnitudes of the eigenvalues, and we also know the U. Remember, B, I still haven't solved the problem. I know this, and I know magnitude of this. I still don't know this. Okay, that's where we are at right now. So let's go back. We have X, which we know is B times N, but B is U lambda V transpose. So let's just regroup these terms this way. Okay, it doesn't mean I know these things. I'm just doing algebra here. That's all. Okay? We regroup these terms. So, but now I do know this, and I know the sign of this. So what do I do? So I can call Y. I can take this X and pre-multiply by the magnitude inverse on the diagonal. That's what we're calling lambda tilde. Lambda tilde is just the magnitudes of the lambdas. Okay? Pre-multiply by lambda inverse and U transpose. So what is this? So if I do that, So if I do that here, we will get U transpose hitting this and lambda tilde inverse. This U transpose gives an identity. Okay. This lambda tilde inverse lambda gives an not identity, but an identity matrix with plus minus ones on the diagonal, which is what we'll call I tilde. And this V transpose is there and N. Okay. Are you good? So far, we are just using what we have learned. Again, stop me if something here is not clear. Yeah.
A very silly question. So we started by this lower triangular matrix.
Yes.
And that can only have come from an SCM. We need to know the SCM to get the.
No. We can re-index the variables such that the matrix A is lower triangle. Such that, yeah.
So I've had this wrong impression that someday we need to know those equations that constitute the SCM, and if we have the SCM, we have.
No, we don't need to know it. I'm just using that argument to say that I minus A inverse is invertible. That lower triangular is just to say that I could do I minus A inverse.
Okay.
Why should the inverse exist? Because by re-indexing that happens. So even if I change the indexing, the inverse is the inverse. So
we don't know what the SCM is, but we know it is an SCM, therefore it's a DAG. And the DAG structure gives lower triangle.
And therefore, this is invertible. I did B. When I wrote X equals Bn, I'm assuming I minus A is invertible. This is the proof to say that I minus A is invertible. That's all. I don't know B. Does it make sense? Yeah. Good, but that's a good question. Yeah, I'm not making any assumption on knowing this here. Okay.
What is I tilde? Like,
yeah. So let me come back once more. Let me do this. I did it, I think, a little too fast. Look at this. So you're good up to this, right? This is the definition. And I also know U and I know lambda tilde, meaning I know the lambdas up to sign. I don't know where I have a plus minus because I have lambda square. When I take the square root, I don't know whether it's a negative or a positive. So I know the eigenvalues up to a uncertainty in the sign at this point. Okay. So what will I do? I will look at X. First, let me pre-multiply X by just U transpose. Let's just do just this first. Forget this for a second. Okay. If I pre-multiply X by U transpose, then this goes away because this is identity. So I get lambda V transpose N. Now I'll pre-multiply that by what I know about the eigenvalue inverse. Okay. So now I have, if I got the signs exactly, this will also be identity, lambda inverse times lambda. But I don't know the signs exactly. So on the diagonal, now I have a plus minus. It's not all ones. Some could be minus one, some could be one, because I might have got the signs wrong. So that's what I tilde is. I tilde is a diagonal matrix of plus minus ones. Somebody else had a question here. Okay. All right. So is this, so I'll now combine this I tilde and V and call it V tilde. So V tilde is the V's with some sign flips. Okay. At some locations. Okay. So now what we have is we have access to Y. Okay. Of V tilde transpose type N. And I need to learn V tilde. This last step is computationally heavy and a bunch of heuristics. I'm just going to tell you the property. There are different algorithms to do this last step. Suppose now I have a CI tester. N is not Gaussian. It is zero mean. It's unit variance. So its joint PDF is not circularly symmetric. V tilde, if I now let R be any rotation of this, let me hit Y with a rotation matrix. Let me look at Z is RY. Search over all rotations. Okay. For each rotation, this is a super expensive step. That's why there needs to be a whole bunch of other things. I'm just giving you the principle. How you actually implement it may be a different game. Okay. Hit Y by all every possible rotation. For every rotation, check whether RY are independent across components. Non-Gaussianity implies that R must be V tilde transpose inverse. V tilde actually the unitary, so it should be V tilde. Because N is independent across components, and when I rotate it, they'll no longer the non-Gaussian. So Bernardo, hopefully this answers what property we're really looking for when it's non-Gaussian. So if one component is Gaussian, is it good enough? I'm not sure. But we can go back and check. Okay. So that is really, so if you find an R such that the components of Z are independent across mutually independent across covariance, then you have found a V tilde. With Gaussians, this will not work because Gaussians are rotationally symmetric. Okay. Yeah.
What if I have a rotationally symmetric exponential decay instead of Gaussian decay? I can construct a joint PDF.
So that's why I just put non-Gaussian. You can read the paper to say exactly what they're assuming. Okay. Yeah. But now you see that's why I wanted to just focus on the property you want as opposed to that word. Okay. You basically want to be able to rotate so that the only way you can get independence across components is by hitting it by the correct matrix. Okay. That's really the property here. So yes.
If the noise is Gaussian, we don't have any value of D.
We can't. This algorithm will not work. We'll not find V tilde, and so we cannot find anything. Okay. The search over rotations and associate testing is extremely expensive the way I have described it. There are lots of heuristics, some information theoretic heuristics there are a bunch of other things you can do. There's a rich literature here. I'm not going down that road, but I'm just saying that at least you get a flavor of the type of algorithm. That's really my goal for both these parts. Not telling you exactly state of the art, but yeah.
Do you have any comments about the computational complexity of two algorithms in ECE and ICA? Is there?
Yes, well, it depends on what heuristics you have for the second part. I have put much more structure, so the second one could be much simpler. But the way it's written here, it doesn't look that much simpler because the last step of the search. Okay, continuous search over.
That's going to be in the rate.
Yeah, so you need to, but suppose you have some more conditions there, then maybe you can do something interesting, so on. So, but at this point, it's sort of heuristic world we have come to. Yeah.
Is the unitary condition for V tilde obvious? Because V, we can say it's unitary.
So, but hitting V with a ±1 matrix, identity matrix is also unitary. If I take a unitary matrix and hit it with a matrix of ±1s, that matrix is also unitary. We can look at this offline. Okay. Yes.
When you don't have that assumption about the rotation symmetry, can you just add noise to the data?
You are given this data, so you are given this model. It's not that there's no gem. You're saying if you could do some active sampling, that's a completely different world. I'm just telling you the base algorithm. Somebody has given me this data X, right? You've got infinite samples from this joint distribution. It's not that you're basically saying I need to somehow modify my sampling of the joint distribution, but that's a different distribution. Maybe, yes, you can, but I'm just giving you the base case here. Yes.
The only place where we're using CA testing here is here to do the rotation.
Everything else was all linear algebra, just classic linear algebra. And this idea actually goes back to the 90s. That's what is ICA. ICA is used as this is ICA. What I've described here is ICA essentially.
So you have U, lambda, and V, right? So you got U and lambda without too much work with just linear algebra. You have to do so much work just for V.
Exactly.
Are U and lambda alone somehow useful?
I don't know, but look at this. If you want to learn the structure, no.
Not for structure, but
I don't know. Maybe. I don't know. This is not things I sort of work on. So I'm just trying to give you a flip. Maybe, but I don't.
So why is retailed rotational matrix? Like, why should we?
What is so because the unitary matrix is just a rotation. Geometry of a unitary. What is a unitary matrix? If you hit a vector with the unitary matrix, it's a rotation. That's the geometric interpretation. So that's the geometry. So I'm trying to derotate it. That's the
rotation and inversion, mirror images.
Yeah. Yeah. Actually,
that's why the plus minus one preserves unitarity.
Yeah.
And you say you have access to Y. How do you have access to Y?
I have access to Y because I have access to X and I have access to U and to lambda tilde. I've learned U and lambda tilde by this point.
How do you have access to X?
X is my data. X is my observations. X is my data. Did you see what I'm saying? I started with, let's go back here. X is the samples from X1 through XD. Is the vector of, it is my, X is what I can observe. I have many realizations of X. Let's say infinite realizations of X. So for each sample vector, I can do this translation to find now vectors Y. Shiva, you had a question? No. No. Okay. All right. So it's 10:51. Good. That gets me to the end of learning. The next section is with dealing with latent variables and instruments. Okay. So maybe instead of starting this, should I go for another 7 or 8? Maybe I should. Maybe we can stop now and we can, people here can pick up their lunch and then we can continue. So let's say this is 7 minutes, 15, 20. Instead of doing full 20 minutes, we can do a little less. We'll start at 11:10. Okay. It's about 17 minutes. So I'll get back online at 11:10. I'm muting right now. Thank you. Okay. So I'm continuing from where we left off. So they're moving to the next set of notes. This is on dealing with latent variables or instrumental variables. So IVs. This is from chapter 9 in the Elements of Causal Inference book, and also some papers which I'm going to talk about in a few minutes. Okay. So before I talk about what an IV is, I want to talk about the key idea, and I want to do it so that we can do the calculations explicitly. Hopefully the sound is coming through. People on, I just switched on the mic. I just want to make sure everything is okay. If somebody could just let me know, that would be awesome.
Yep, sounds good.
Thank you. So I'm going to do it with scalars so that you can see the ideas completely here, and then the vector version are all follow. Suppose you have the following directed model. Okay, Z is Z. I'll just do stylized and then I'll tell you why this is interesting afterwards. Stylized problem is the following: Z is a Gaussian, zero mean unit variance, N1. Okay. X is some linear transformation of Z, but with new noise added to it. X is A times Z plus N is some independent noise. And Y is some linear transformation of X and Z. So C times X plus B times Z plus some independent Gaussian noise. All the noise variables are zero mean unit variance. They're all mutually independent. And everything is scalar here. Okay. The model is clear, right? So now Z is a latent variable in the sense that we don't have access to this. So this is the underlying model, but what you can see is only this box. Okay. And in fact, you can't even see this value C. What you can see, what you can get is samples X1, Y1, X2, Y2. You have an oracle which you can call into this and get as many samples as you want. Okay. You've got infinite samples of X, Y. Is the setting clear? Okay. So the question is, can I learn the value of C in this case? The answer is no. And because there's a latent confounder that affects both X and Y. And we will do this calculation to see that. So what would you do if you want to figure out C? I'll just solve linear regression. It's a scalar linear regression.
So what will I do? I will say that y, I'll say equal to gamma times x. I know it's a linear model, so I'll just try to find a linear best fit. Y, so I will do y minus gamma x, the whole square, the expected value. For those of you who come to the machine learning world, this is the sort of probability way of writing this. Really what you are going to do is summation xi minus, this is what you would do, right? This is the standard way, maybe in stats, you will write this regression problem. Okay, sum of squares and minimize over gamma. Okay. I've just written, because I have infinite, I'm just putting the expectation. That's all. Okay. So you can solve this. You can solve the regression however you, the least squares, however you want, and you will get a solution to it. So yeah, I've done the calculations here. If you trust me, then it turns out that because even though there is no z sitting in here, if you go back to the equations and you write things out, there will be expectation of xz type terms coming in. So the samples just based on x and y, the gamma which you will learn a parameter gamma, and this is related to the underlying parameters a, b, and c, which you don't see through this equation. Okay. Meaning, so if you simplify this further, it is this true value c, but with a bias, and the bias depends on b and a. So going back to this, let's see where that figure is. Yeah. If this edge was missing, then the bias is 0. Again, if this edge was missing, again, the bias is 0. The problem happens because z can affect both x and y. Okay. So this is what gamma, you'll be able to observe gamma, but gamma is this, and you don't know a, b, or c. So there is no way to figure out c exactly. Okay. This is the problem. So is the problem, hopefully it's clear at this point. So a cool way to deal with this is something called instrumental variables. Suppose, now I'm going to make a supposition. We'll see why maybe the supposition is how the supposition could be true. Suppose I have access to another variable t that affects x in some linear manner with strength d. Again, I don't know d. Okay. The samples I have is t, x, comma, y now. I still don't have z, but I have samples of t, comma, x, comma, y. Then is there hope of learning c without bias? That's the question. This was the previous model where I had samples of x, comma, y. Now I'm saying that somebody has given me triplet of samples, t1, x1, y1, t2, x2, comma, y2, and so on. These are the samples I have. Okay. I don't know any of the parameters, but I have a large collection of samples of t, comma, x, comma, y. Is it setting clear? Okay. The crucial thing is there is no edge here, there is no edge here, and all that stuff. Okay. Now, can you learn? Again, I don't care about D. What I care about is to learn C correctly. Okay, that is my goal. And so we can do this. This is called, then T is called an instrument. Okay, or an instrumental variable. And the famous algorithm is 2SLS for this, or the two-stage least squares. What is the algorithm? First, I will fit X on T, or fit T on X, whichever, I forget how the language is, whatever the fit for. Solve this least squares problem. X minus alpha times T whole square. Okay. So I will try to learn this parameter. It's a linear model. And there is no confounder, nothing else. So you can believe that I can learn D. Correct? With enough number of samples, I should be able to learn D should be equal to alpha star. It solves this problem. You can do the calculation and check, but it seems very reasonable that that's what should happen. Okay. Now, next, I will ignore X and try to find T to Y. I will solve this problem. I will just try to fit. I will solve this least squares problem. Y minus ST.
But you don't have edge from T to Y.
So what? I have data. I just solve this least squares. Why T can somehow in some manner it affects Y. So that means from the data I should be able to just solve least squares. I'll just blindly solve least squares. I know that there is no edge, but I'll just blindly solve least squares. That is allowed, right? Okay. So if I solve that least squares, I have written out the least square solution. Maybe I should, so these are the equations now. Okay. You can solve the least squares. You will get that the least squares coefficient is C times D. You will actually get that. You can do this yourself. And therefore, you can estimate C by taking the ratio of these two things. This is an unbiased estimator. This is a cool idea. This is called 2SLS. Okay. Or two-stage least squares. Okay. Even though there is no edge from T to thing, the regression will give you C times D. You seem very, do you believe, you want me to show the calculation to show that you get C times D? Okay. Since you want that calculation, let's actually show that. Okay. Somebody asked. So let's take the time to actually do this. This is what I want to solve, right? Y minus ST whole square. So I want to, what do I need to do? I need to estimate T expected. So if I want to solve the least squares coefficient, if they're all zero mean, so that's why I'm not doing covariances or variances. I'm just looking at correlations and second moments. They're equivalent because everything is zero mean. Okay. So look at expected value of T times Y divided by expected value of T square. What is the expected value of T square? Since it's zero mean unit variance, E of T square is just 1 in our model. E of T times Y is Y is nothing but the C times X plus B times Z plus N3. So I substitute that in. So I get T times X plus T times Z plus N3. Okay. Now T and Z. You can argue here what T is. What is T? Just N4. Z is just N1. They're independent. So the expected value of the product is 0.
But you can think of it as collider because it's collider.
I'm not doing any, I'm just doing undergrad prob. Okay. This is independent zero mean Gaussian. This is independent zero mean Gaussian. The expected value of the product is the product of the expectations is just 0. Okay. Similarly, N3 times T. N3 and T are independent Gaussian. And so again, this is 0. So the only term that's left is T times X. If you now substitute T times X, this is N4. You can do the calculation. There's the only term that's left here. There's a C times. If you do this calculation, you will get this D times T square. All the other terms cancel. So you'll just get C. And the expected value of T square is 1. So you'll get the numerator as C times D, the denominator as 1. So just solving least squares gives you C times D. Now I solve the previous least squares to find D. Yeah.
This is essentially like intervention, right? You had the 3-node graph.
This is not an intervention. I have data on this. This is not, I'm not setting X to something because it's not setting the value of X. It is affecting it in some way.
So how are you going to, suppose I have only X comma Y data.
Good. You cannot do this. But suppose there was a T. First, that's why I want to start with the abstract and tell you how this is used. Okay. I decided to do this backwards so that we can see what is going on, and then I can tell you why this is useful. Okay. So I get one least squares gives me C times D. The other least squares gives me D, and say I can find C. Okay. Without bias. So why is this interesting? So this is this is one of the examples. I give you all the references towards the end. So I want to check whether smoking affects health. Okay. This is my question. You think right now it is obvious, but if you go 70 years back or 60 years back, there's super controversial, the studies for this. And there are a lot of very, very dirty politics in this, which I don't even want to talk about in this recorded setting. Okay. So there is smoking, there is health, and there are some things, but there may be, if you just solve a least squares on smoking versus health, maybe it shows that smoking affects health, but somebody could argue, no, it's some confounder that's really causing this. Meaning, maybe there is something that affects both smoking and health, maybe depression. And maybe depression is what is causing the health you to smoke, as well as causing your health situation to worsen. Okay, it may have nothing to do with smoking. How do you refute these kinds of things? Okay, this is the question. Okay. So Now let's build a causal model. Again, this is also controversial because I'm putting in another model and some other assumptions, but it's a different set of assumptions. Okay. So this is the model which we potentially have. And we want to find the strength of this. Ideally, what we would want to do is to do here, giving everything we talked about here. Forget this business. We'd like to do here and figure this out. That's what we did in the kidney stone experiment. Here, we don't have access to C because we don't even know what these confounders are. I'm just saying maybe it's depression, maybe it's something else. So there's no way to actually, and we can't, it's not even clear how to do an experiment here. Okay. People have, but it's a priori not exactly clear what is to be done. But suppose you had access to cigarette tax and tax changes over time. And you posit the following model. The tax level affects smoking, but the tax level does not affect other depression or other confounder. Again, this is an assumption. Somebody might argue, no, increase in tax makes me more depressed. Okay, maybe. Okay, so I'm trying to be transparent here about what the assumptions are. But suppose you posit that the tax does not affect these confounders. Okay, then we can actually test. We can actually learn this thing. Because now I have a new data set. I have the data set of tax, smoking effect, and health. And now I can learn this product using 2SLS. I can learn this and actually I can try to find the strength. And people have done these kinds of things. You can read additional discussion. So a paper which you want to look at, a cigarette price provided better estimates of effects of smoking in Journal of Clinical Epidemiology, 2004. You can look at these papers if you're interested in this line.
So you were saying how to estimate that we should do that S, right? But that's not possible. But then suppose I was able to do S, then you would do that, you would draw the extended graph. And that looks exactly like this, right? Except that the T would be a binary variable, the ideal.
No, but this would not be there. When you do, it's not exactly this because this is gone. You delete the parents of S. So it is not the, so do it. This is not do. This is something else. The parents are, those edges are still there. But it doesn't matter because we are doing a ratio to actually eliminate the bias. Okay. So it is not the same as do.
I see.
Do you see what I'm saying?
No, actually, when you did the do and you drew that extended graph.
Yeah, let's do that.
Graph,
this one goes away. Edge, right? No, when we did the I, this edge was deleted and this set. Let's do the atomic intervention. I atomically say smoking equal to 1. I set this to 1 and delete this edge. That's not what we are doing here. Yes.
Does anything change if we have multiple?
No, these vector versions. That's why you can go back. It's just 2-stage least squares. You can get vector versions of this to work.
So I have a question. So what would doing S like
what does it mean physically?
Yeah.
It means that somehow I can disconnect your brain and every other part of your body from your lung and smoke the lung and see your healthcare, I guess. I'm not sure. You need to smoke. No, but that's not enough. But maybe the fact of forcing, but you have to somehow, it's not enough to just force you to smoke. You need to cut these edges.
It would be a randomized control trial where you, instead of a drug, you are giving cigarettes to people and asking.
Yeah, you need to. Yeah, I guess that's a better answer than what I'm saying. Yeah, that's true.
So like doing.
Sorry.
So it would mean like for every data point that you have in the data set, you would ask the person to like forcefully smoke. And
whether they want to smoke or not.
Correct. So it's more than randomized control trial because in randomized control trial, like you can give cigarettes.
That is what this is. But maybe that this is sort of like that. You can think of this is sort of like that. In that sense, this is exactly what it is. Okay, it's indirect control. Okay, you give them the option, but whether they choose it or not, that's exactly what this is. Okay, that's another way to use this. I'll talk about one more example where this will become even more clear. Yeah.
I have a question. So what happens if we don't have the option? First of all, like if you do like economic policy, for example, right? Either you do it or you don't, right?
A very, very good question. And that brings me to the next point. These are called natural experiments. Okay. So the history of IEEE is from 1920s. There are applications and basically something called natural experiments, which is using IEEE to overcome missing variables by appropriate variable selection. So if you can find a variable which occurs in natural social settings or because of government policy or something like that, then you could essentially answer this question. Okay, so a really nice paper which I would suggest you read for this is the following: Instrument Variables and the Search for Identification from Supply and Demand to Natural Experiments by Ankrist and Kruger. There's a survey in 2001, and Ankrist was one of the Nobel Prize, was the 2020, one of the recipients of the Nobel Prize in 2021 in econ for use of natural experiments and causal reasons in sort of economic settings. Okay, so this IV lies at the heart of some of the methods that he and his collaborators have used. I'll give you one example, which I think is an interesting story here. It is taken from that paper. T is a Vietnam. The question which we want to ask is the following: does military service affect future earnings? Okay. It's an interesting policy question. How do you test this kind of stuff? The problem is there are confounders that could affect both military service and future earnings. Maybe you're from a social setting where you want to go to the military, but the same setting inculcates a certain discipline, which makes you work harder and you earn more money or less money or whatever, right? You can make up all sorts of possible confounders which could relate both military service and future earnings. But in the Vietnam draft for the Vietnam War times, there's a lottery-based people were forced to go to the military. And this lottery clearly was done by the government, had nothing to do with your social setting. It was something completely different. So that T is the lottery, X is whether military service, and Y is future earnings, and C is the confounder. So 2SLS was a way to sort of test these kinds of things. So now you see what I mean by it's very useful in for social questions, economic studies. When you've got a large number of even unknown confounders, but you still want to make unbiased estimate of treatment versus effect. These kinds of things. All right, so you can read that also. There's also, this thing goes back to a paper by Ankrist in 1990, and you can look at this survey articles in 2001 above, and they're much more on IVs. It looks like a magic black box. Okay, now I'll tell you the downside of IVs. It's a ratio estimator. Concentrations are miserable. Okay, that's for people who have done estimators with ratios. If the small perturbation denominator can lead to huge confidence bounds on the outside, on the numerator. Okay, so let's say this varies by, this is actually 0.1, let's say truth. I change it plus minus, I could get multiplicative effects depending on the numerator if I get small perturbation in the denominator, depending on the actual values. And so distinguish between this, one issue here is then distinguishing between this, maybe there's a very, very, very weak effect, which we don't even know. It's very hard to figure those kinds of things out. So a lot of this literature will have to justify this model extremely carefully and make sure this, because finally you're in a finite sample setting. Okay. So there are also papers which talk about how does public policy in terms of food coupons help, things like that. So IVs would be sort of, you decide some cities to run this on, and then people there may or may not take up this. These things, there are so many confounders, and the size of sample, it's not clear, that you should be very, very careful when you're using these methods because finite sample issues. I'm just giving you sort of the high level story here. If you're interested in this, please look at the literature.
So here in the noise and denominator is coming from the noise in the instrumental variable.
The noise in the denominator is coming from the noise here. Exactly, this estimation noise. So you're trying to estimate D. But if you have D plus minus epsilon divided by CD plus minus delta, this is basically what we have. So what is your error? It is, this is okay, plus delta by D plus or minus epsilon. Say D is actually small. Now this depends on, actually, it's not some scale invariant. So let's say D is 0.1 or 0.01. Then delta is multiplied by 100. And if epsilon is, right, a small change here will throw things off really badly in the numerator. So your estimates of C may not, maybe it's better to just do a biased estimator directly and just live with it. Okay. I'm not saying that it is, but I'm just saying what are the issues that can happen. And by the way, these are not issues that I'm just making up. There are papers on all these kinds of things.
So, ma'am, my follow-up real question I wanted to go to was that suppose we had multiple options for T. Let's say we are trying to, how do we
there's rich literature on choosing instruments. So I would say go to Anchor's. The tutorial is a good one, but there's much more recent stuff. I was looking at some papers in the epidemiology literature more recently, like 2018 and 19. There are some very nice papers. What if it's not Gaussian? Then it makes life is much harder. Okay, yeah, because many of these treatments are categorical or binary. So it's much more. I took the simplest possible setting I could to show you what the idea is. That's about it. But there's way more literature. There's a paper which I really like from 2019. I can give it to you offline if you're interested. Yeah.
So at the end of the day, when we run this over data, we get some number for C, right? It can be wrong or whatever. How do we? I mean, it's not zero. It's obviously something. Even if it's zero, we're gonna have some error. How do we actually decide if it's there or not? Like in reality,
I mean, but this is the same question I'm asking. I done regression, I get a value, and I'm going to use that to make decisions. Why do I believe that? Whether it's this or not, you have confidence bounds. You have then you know all the usual statistical answer is my answer to your question.
For example, in the cigarette thingy, like people actually see.
Yes, but then the other people have posed some other model. This model hasn't answered, is not the be all end all. This is yet a preponderance of different models giving evidence is finally to convince a bunch of people on social things. Look, right? The one number. So we are not talking about I'm making a decision to transmit or non-transmit. You're talking about people's behavior. Okay, it's a completely different game.
Yeah. So given the estimator, the denominator was B plus the variance in that term, right? I don't know if this is correct, but I feel the variance is a function of A as well here.
This is not. This one is not.
No, the variance in the estimator.
But the numerator, yes, because this estimator will have everything put in there. This estimator has B, this one, if you want the bias of this. So you're asking, the variance in A, will it affect? Yes, of course it does. Because the distribution of X changes. Yeah, the variance, but I'm just talking about the mean here.
Yeah, no, so where I'm trying to get is, if the variance is low, which is when our estimate is good, better and better, it's sort of getting closer to the case where you're doing atomic. In a way, you're deleting the pair.
But I can take larger. Suppose I could do many samples, then I can beat down the variance. So it's not equal. The infinite samples, I still have issues. Here with infinite samples, there are no issues. So it is qualitatively different. See, anytime we talk about all the atomic interference, all the infinite sample setting. Okay, here in the infinite sample setting, there's no issue. So it's there, that's a mean issue as well. Here, there's no mean issue. It's a variance. So it's moved to some other place, the problem. Okay.
So if we had an intervention here, even with infinite sample, we would have an issue here.
Well, yes, because depending on I'm assuming faithfulness and given this graph, yes, we could do various. So you're basically saying if I could intervene here, which means I delete this edge, delete this business. That's what I'm doing, right? Then I could, and have infinite samples, then I could find the average causal effect, exactly what we did. That's fine. That is fine. There's no issue there.
So instrumental variables fit best where we have a latent variable that could be confounding and we can't do a do of it. That is.
Which is why natural experiments is sort of a powerful example. This idea of instruments goes back to 20s in some form or the other. 1920s, not okay. Just to be clear.
So actual randomized control trial, you would like to on this say to It will be all the different confounded variables. You would like to have enough number of them in both, let's say, treatment 0 and treatment 1. Practically, how do they? I don't know.
I can give you sort of look at those models and I can use some concentration equations, but how people do this in practice, I'm not really sure. I mean, how they actually run these things, I don't know, other than I've just read some of the papers in the space, but since I don't work in this area, I just wanted to sort of highlight various things. So this is what I know about this. Yeah.
Maybe it's a dumb question, but given the data, are you able to identify where you will find, well, where there could be latent variables?
Not immediately. Unknown. You're asking, are there unknown unknowns? And that's sort of.
I'm asking if you're able to detect them.
That's what your question I can rephrase as there are no unknown unknowns. That's what you're stating. Okay. Which seems like a very strong statement. So.
I mean, even if T had a path to Y, we could have handled that in these questions. Right?
Yes. If you had, if this was there, then not clear. Not clear. Yeah, we have issues. We need to find something else. So any other path, this method will not work. Okay. All right. So now you've seen two SLS. I have another 20 minutes. So let me start the next section.
How is it? What is definition of instrumental variable? Just a variable that affects
T.
only one thing.
Yeah. This is the, you've got this as the base model. This is the instrumental variable.
And oh, you said they came up with it back in the 20s.
The first instrumental, this kind of model goes back to 1920s.
We assume that somebody gave us this variable. We are not creating.
Well, you have to find such a variable. If you are an economist or sociologist, you need to look at the system and figure out if there's an instrument, how to design instrument. There may be multiple instruments, which is the strongest instrument. All that kind of stuff is part of this study.
It's not possible to look at the data X1 and X and Y and create a new variable. That one seems to be impossible.
That's an active. Can you construct instruments for doing something? Potentially, that's also possible. Yeah.
Are there instrument variables with respect to effect and not cause? And
what does that mean?
For Y.
T to Y or Y to T.
But how is that going to help me learn? My goal is to learn C. My goal is to see whether, let's step back. Our whole point is to figure out C. Okay, that's all. Huh?
In that case, Y would have been a collider.
Exactly.
Observing Y would.
Exactly. So my goal is to figure out whether there's a causal effect from C to Y, X to Y. Okay. So anything else is not useful for answering that question. Yeah.
Would it be possible to use existing variables as
instruments? Yeah, people have.
Okay.
That was that example of that Vietnam era thing.
No, but I mean, like, add edges.
You have to do new experiments. People have tried this. There's a recent paper, maybe 2 years back, doing instrument variables to do some ad study in online ad placement. Okay, or 1 or 2 years back. So how do you do an experiment? So I don't remember the details now, but it's I have some ad placement strategy. There are a whole bunch of different placement strategies, and you want to find the effectiveness of one of them. It's either a NeurIPS paper or it's in some machine learning conference. There are papers in the last couple of years on can you do some instrument studies. I don't remember the references now off the top of my head, but I can pull them out. It's somewhere on the computer. Yeah.
Still waiting for the answer on the military thing.
I don't know the answer. I don't give you an answer. I just tell you frameworks. Okay. All right. So let's move on. So this instrument, and now I've finally moved to the last piece. I have about 15 minutes. So far, let's step back. What have we done? We started with the directed graphical models, talked about the plumbing for that, talked about structural causal models, adjustments, do calculus. So that was that covered that full story. But that's all the infinite sample forward generative model. Then we looked at the inverse problems. I want to learn this structure. And this we saw, because CI testing was the black box which has been used extensively through that. Okay. We did an aside on a little bit just to give you a flavor of how to deal with latency, but that's really an aside. That's not on the main line. So I want to come back now to the main thing, which to close the story, we need to talk about CI testing, because that is the black box that has been used all the time. So my goal in the next 15 minutes to start thinking about hardness. I'll also continue this tomorrow, and then talk about various CI testers and how these things are done. Okay. So now this is sort of moving out of causality and going into statistics at this point. Okay. Because I'm not thinking about graphical models or any such thing. The question always for the rest of this thing is X and Y condition independent Z, yes or no? That's all I'm going to talk about for the rest of this lectures. Okay. And I'm going to start with this following paper, Hardness of CI Testing, the Hardness of CI Testing and in Generalized Covariance Matrix by Shaw and Peters. Shaw is a professor of statistics at Cambridge, if I'm not mistaken. Peters in Darmstadt, if I'm not mistaken, Germany. But this is a really cool paper. I like this. So let's start with this one. So the problem is, are X and Y condition independent given Z? Is this easy or hard? What does it even? So this question has not been cleanly answered, I think, until this paper. Okay. So that's why I think this paper, and what does easy or hard mean also, I haven't described. So let's get to that. Okay. So the setting here is X, Y, and Z are vectors of certain dimension. Okay. They're continuous random variables. Okay. What do I mean by that? That their induced measure is absolutely continuous with respect to the Lebesgue measure. I'm sorry, from now on, I'm going to be at a little more technical than what we have been doing so far, because these things are actually important. Okay. So I'll try to describe these things in other language as well, but I want to sort of state these things as well. What do you mean by continuous random variable? That it has a PDF. Let's look at scale. And so you shouldn't have delta functions. You shouldn't have impulses. You shouldn't have PM. You shouldn't have atomic masses. Okay. And that's really what this absolutely continuous with respect to the Lebesgue measure means. Okay. That it's that a PDF exists. So that's the assumptions here. Okay. So the set E0 is a set of all joint distributions on X, Y, and Z. Okay, such that these joint distributions are absolutely they're PDFs. Okay, that's what I'm considering. I'm considering all joint distributions over X, Y, and Z, which are PDF. Furthermore, E0M are all sets of joint distributions which have PDFs, such that they are supported over -m plus m. So it's finite support. These are all random variables between -m to +m, say uniform or whatever, over -m to m. Okay, uniform PDFs. So, okay, that's E0M. So these are, so far I've just described all PDF, all distributions I care about on X, Y, Z. P0 are all those joint distributions such that X and Y are condition independent given Z. What does it mean? Fxy given Z equal to Fx given Z times Fy given Z. That's what we need. Okay. The densities, product form. And Q is everything else. Okay. So P are the conditional independent ones, and Q are the ones that are not conditional independent.
What's epsilon 0?
It's a set of all joint distributions. E0 is a set of all joint distributions. Okay. E0 is a set of all. This is meant to be script cal E, math cal E. So I just wrote math cal E this way. The script E0, okay, is set of all joint distributions. E0M is truncated to meaning it has support only between -m and not truncated. It's support between -m and m. The distributions from that which have the support. P0 is a set which are condition independent. Q are which are not. And similarly, P0M are, those are conditionally independent and supported between minus MM, Q0, conditionally not independent, supported between minus MM. Okay. So this is the setting. Let's go down this. Let's see what is the question we are trying to answer when we say are they condition independent or not. Really, we are trying to solve a composite hypothesis testing problem. And if you haven't seen, so most of you, at least in an undergrad class, would have seen a binary hypothesis testing problem. What is the composite hypothesis testing problem? The null hypothesis 0 is that X and Y are condition independent given Z. Okay. What does it mean? That P is chosen from one among this family of distributions. It is not a single P anymore. It can be anything from a set of distributions. Okay. And the alternative is X and Y are not condition independent given Z, which means Q is chosen from this set of distributions. I'm going to go slowly here because I'm introducing way more formal notation than what I've been doing till now in this short course. If anything is not clear, just stop me.
So the null hypothesis is then for all the distributions, for all the probability measures? No.
Somebody picks one P. The question is, you are given, okay, so let me ask, the null hypothesis, so what, let me ask you, let me do the next step and then I think your question will give it. Okay. You are given N samples, IID, XI, YI, ZI. You want to figure out, you want to devise a test, psi N, which takes those samples, those, so you're given N samples, N vectors essentially is what you're given. And you can randomize if you want. You can pick some random independent random variable if you want. Okay. And you want to return 0 or 1, meaning are these samples from here? Meaning, did nature pick one P from this class to generate those samples? Or was the sample from here? Meaning the nature picked one Q from here and generated those samples. Is the question clear? Good. So this is basically what you want to devise, a test. So this is what we mean by a CI tester, right? In a given data, you want to check CI. Now this is the first time I've sort of formally told you what a CI tester is. Okay. You need to solve this hypothesis testing problem, this composite hypothesis testing problem. Okay. Till now, I've been sloppy about what CI testers actually mean. Okay.
I'm still not about composite. If null hypothesis is not true, then that's not just.
No, because the null hypothesis is not one hypothesis. It's composite in the sense that there are many possible null hypotheses inside the one quote unquote this null hypothesis. It could be P1 or it could be P2. It could be any one of these P's. Standard hypothesis testing is there's a distribution here. You want to distinguish between two distributions. Here you're trying to distinguish between a partition of all a set of distributions. That's what I mean by composite hypothesis testing. Yes.
So the central question here is that between the two sets of distribution, which one generated the data that we are observing?
Yes.
So one thing that we often use while modeling observed data are mixtures of distributions. Can't we also have a third case that the data was actually?
But any mixture, if they're conditionally independent, that will also fit in this. If these all distributions are they're conditionally independent. If you took two distributions that are conditionally independent, they're mixture, that's a third one. That's also in P.
Have a mixture of like some P and some.
No, but that will not be. Either it will be conditionally independent. Finally, whatever mixture you generate is either conditionally independent or not. In which case, it goes to one class or the other. Okay. So you have finally just got two classes of distributions, whatever you do. Those which result in conditional independence and those that don't. And I want to figure out which one is mine from. So there are two things which we care about when we're doing this, the level and power of tests. I mean, for statisticians, this is boring, but I'm going to go through this anyway, because at least I'm not a statistician, and these things were things that I needed to think about when I first read this. And I presume at least for some of you, these things will be useful to go through. So level of test is the following. It has a valid level alpha if the following property holds. Let's go through this. Look at so you pick a first let's pick one P, which means it's a conditional hypothesis. So from this class, we are picking one particular P right now. Okay, just start from there. Somebody has picked one P. And with that P, you have generated data, n samples. And now you ask, what's the probability that your test results in 1, which means it's saying it's not conditionally independent. It's giving an error. Okay. You want this to be small for a good test, correct? But you want something stronger. You want this to be small over all possible selections of P. Okay. So this quantity is called the level. It's the worst case type 1 error, quote unquote, if you are doing binary hypothesis testing, okay, over your class of P's. So again, picking a P means that you're generating samples xi, yi, zi according to P, IID, and samples. Using that, you create this test, and that test, because of the randomness, it will either be right or wrong, and there's a probability if it's wrong. Is the level clear? What I mean by level?
So it's technically alpha n, right? But you're thinking of n as a constant. So
where is alpha n?
Alpha. The alpha should actually be alpha n, right?
I'm not going to let n go to infinity yet.
Right.
I'm fixing an n, so it is all n dependent. Okay. Given an n, the alpha is called the level of the test. This is basically the analog of test is wrong given head 0 in binary hypothesis testing. Okay. The other one is the power of the test. Okay. What's the power of the test? Pick a Q, which is actually x and y is not conditionally independent. And the test is correct. It says that it's not conditionally independent. And now, because this is the correctness, the worst case is the other way. I need to take the minimum over all of them. Even that minimum should be large. So I'd ideally like alpha to be 0 and beta to be 1. Right? That if you look at these two equations together, I want very low level. I want this to be 0. And I want very high power. That's the best case scenario. Okay, good. So we have two quantities, level and power. So first, today I'm going to, because I have only 5 minutes, I'm going to state the results, and tomorrow I'm going to give the intuition and a sketch of the proof. That's tomorrow's thing. Okay, I think this is just such a beautiful result of what they have. So their theorem 2 in their paper, with theorem 1 is the following: given any n, any level you want alpha, and any m, and any randomized test field for which the level is small. The power is also small. Okay. In fact, this is worse than the power is small. It's soup, not even inch. It's even worse. Okay. The power, remember, was the inch. It is saying not just the inch, even the soup. It's way stronger than the power is strong. It's a hopeless problem. It's saying CI testing in general is a hopeless problem. Okay, that's the first result. I'll talk to this once more tomorrow. Okay, today I just want to tell you the results before we close. So that's their first result. There is no test for condition independence that can have low level and high power. The second, you may think it's a distance property of some distributions. The second very interesting result is the following. Look at any two distributions P and Q. Forget about whether they're condition independent or not for now. Okay. Then there's something called the total variation distance, which is the following. Pick any set A, find the probability that your random variables under P lies in A, minus the probability that the random variables lies in B, and search over all Borel sets. Right? This is the total variation distance. For you, many of you might have seen total variation distance on delta function. This is the TV distance for more general distributions. Second result says, pick any P you want. Then there's a Q that is actually far away from P. Okay? Meaning that there is, therefore, so what does that mean? What's the implication? I'll do this one more pass. It says that there is no P satisfying XY and Z, XY condition independent of Z. P is, remember, this property that actually close in total variation distance to a specific Q, which will be constructed. So it's not that there somehow you're coming up with two close distributions. Okay, in total variation distance, they're very far away. again, these are subtle. I'm doing this very quickly. I'll do this one more pass. But for any Q, including the one constructed above, which is far away, CI testing does not have reasonable power. So essentially, the hardness of CI testing is not because of total variation distance. Something else is going on. Okay. And tomorrow, I will watch the roadmap. I'm going to repeat these statements once more. So, but hopefully you have some time to digest it today. And then give you a graphical reason why. I'm not going to prove their thing, but there's a very nice construction shows you what is at the heart of these issues. And they're also useful because it tells you what you need, what are bad things that can happen, how to deal with it when you're actually building tests. So that's why I wanted to start with this negative result before I went to positive results. And then I will go through a bunch of sort of different types of positive results. How do you do CI testing? Kernel methods. These are powerful classes. This is one. Some randomization, something called knockoffs. Randomization methods. Something called permutation tests. This is an example of that. So I want to talk through various types of how you would test this, what are the ideas, and that will bring me to the end of this lecture series. Okay. So I'm stopping at this. I think there's a natural place to stop. Tomorrow I'll sort of go through this. Thank you.